Now, having gone through the content of our electrolytic cell, it is very important for us to run through some of these activities so that we get things in correct perspective. So now we will run through the activities. You remember the rule: pause the video, answer the questions, and when we mark, you just mark as well. Please, it is important that you answer the questions before we run through. All right, let's run through now. Let's run through our solutions very fast. We're going to move swiftly in this session. 7.1 says define an electrolytic cell. All right, we know that an electrolytic cell is an electrochemical cell. Electrochemical cell that converts electrical energy to chemical energy. That suffices enough to get you your marks. You know, there could be so many other definitions that mean the same thing. If you could write a cell where chemical compound is broken down with the aid of electric current, still the same thing. Write down the names or formulae of the ions present in the melt. Remember, in the melt, actually what we have is Al2O3, which breaks down into Al3 plus and O2 minus. So this is what is required of us to write down the formulae of the ions. And the name, you could, it's either the name or the formula. That is aluminium ion and oxide ion. All right, your oxide ion. Okay, all right. 7.3, write down the half reaction that occurs at the anode. If you go back to our video session, we actually did all this. At the anode, what will help you first? The anode is the positive. So what you have coming to the anode is your oxide ion, which will now be oxidized. So our half cell reaction would be, if you go to the table, you would find your oxide ion, and that is just as simple as that. You get yourself your 2 marks right there. Okay, 7.4, write down the half reaction that occurs at the cathode. Again, which is, this should lead you, 7.3 should lead you to 7.4. What do you have at the cathode? Remember, the cathode is a negative, and you have Al3 plus at the cathode. So what should we have? That's where we have reduction. Al3 plus 3 electron, the gain of electron, and you have aluminum solid. Very, very straightforward kind of questions there. 7.5, calculate the cell potential for the electrolytic cell if the reaction occurring at the anode has an electrode potential of that anode. Remember, that's the oxide. Okay, the reason is that the value of the oxide is not given on the electrochemical table. Our formula would remain E cathode minus E anode. All right, we already know this one to be negative 0.56. The question is, what is aluminum? So we need to run back to our table to get the value of aluminum. Let's find Al. I'm sure you have your table there with you, and you were able to get Al. All right, I found it. Al is negative 1.66. So we take it back there, negative 1.66. So using your calculator, this one becomes positive there. You should have negative 1.1 volts. Remember, we said this cell is not spontaneous. All right. Explain why the anodes have to be replaced on a regular basis. Or we We did explain that at 7. Okay, let's write it down. Remember that your oxide ions are oxidated to oxygen, which reacts with carbon. So we could just have this oxide ions, all right, are oxidized because the question says explain. Oxidized to oxygen, all right, which reacts with our electrode, which are carbon graphite, to form carbon dioxide, which is a gas, a carbon dioxide gas, which is given off. So that alone suffices for us. So if it's given off, we can say the electrode therefore erodes. Erodes means disappears or corrodes away. So they have to be replaced regularly. Awesome. All right, so that gets you 13 marks there very fast, you know. Get those 13 marks in 5 minutes. It's a good question there. All right, let's get another question. All right, let's run through another question quickly so that we have enough. Okay, here's another question. Here is another question that we need to run through. We're going to run through as many as we can for this session so that we get things in the correct perspective. All right. Let's scroll down for us to get the remaining part of this question. And I see here there is a calculation that we need to do, which is a very good question. It's going to expose us to the calculation on electrolytic. All right. Okay, let's answer our questions now. Let's read. High purity copper is obtained by electrolysis using a thin, pure copper cathode and an acidified solution of copper 2 sulfate. This is electrorefining. All right. Now, before we even look at the question, if this is electrorefining, then remember that our cathode must, because an electrolysis, our cathode must be the negative electrode. All right. And our anode is here. Remember, we see at C. All right. So this is the cathode. This must therefore be our pure. You know, we can analyze this even before we answer, and this is going to be our impure. All right. Let's see. At which electrode will pure carbon be deposited? We've already answered that. B. State the relationship between the current I and the mass deposited depicted by this graph. All right, from physics and mathematics, we know if you have a straight line graph, your variables are actually directly proportional. So we can say that the mass deposited is directly proportional. It's a straight line graph, remember, directly proportional to current. And then you get the 1 mark there. The major keyword is directly proportional. All right. When a current flows for 1 hour, 32 grams of copper, okay, we need that, is deposited at one of the electrodes. Would the mass lost by the other electrode be larger or smaller? Good question here. Let me explain this quickly. Remember that what we really have going on simultaneously, what we have going on is this, and at the same time we have this going on. So our full reaction therefore should be that. So whatever is lost, it's 2 electrons and 2 electrons here. Whatever is lost is also gained. So our answer should actually be the same mass, because it's the same number of moles of electrons. So our answer is going to be the same. All right, it's going to be the same. Very, very beautiful question asked there. Calculate the number of moles of copper deposited In the question, we're told that 32 grams of copper is deposited. That's a giveaway question there. 9.4, what is the number of moles is mass over molar mass. We're looking for the number of moles, 32. Now, what is the molar mass of copper? That we can actually get from our periodic table, right? Copper here, 63,5. Good. So 63,5. And our answer would be, if you use your calculator now, your answer would be 0,504 moles. 0,504 moles of copper. That's almost half there. Okay. Now, question. Oh, was that 9.4? No, that was 9.3. Oh, there's no 9.4. My bad. 9.3.3 now. Use your answer in 9.3.2 and other any relevant information. That's very tricky. That's a tricky statement. To determine the average current, we're looking for current. Okay, remember we've got time here, 1 hour. Average current. So we're looking for current. That should be 9.3.2. These 9.3. This is 9.3.2 here. 9.3.3. Okay. One of the things we know is that, look, if we go back to what is deposited, it's copper 2 plus. All right. Now, what we're saying here is this. 1 mole of copper will require 2 moles of electron. But how many moles of electron do we have? Okay, how many moles of copper do we have? 0,504 moles of copper. How many electrons would that need? If we say X and then we cross multiply, X will be 2 times 0,504, and that should be 2 times 5 will give us 10, 1,008 moles of electron. All right. What do we need to do to calculate current? What's the formula for current? All right, this is physics actually. Q equals to I delta T. We were given our delta T to be 1 hour, which is also equal to 3,600 seconds. I'm sure you know that from your physics 60 by 60. Now, we're looking for I. The question is, what is Q? What is Q? In our electrostatics formula, there is a formula that says that Q equals to NE. I'm tempted to write a capital N, and I'll tell you why. Q equals to NE, where E represents the number of charges. Sorry, the charge on an electron. E represents the charge, and that's a constant charge on an electron. We'll see that from the table. And N represents the number of electrons. This is a charge quantization in grade 10, charge quantization. Q equals to NE. Now, how are we going to get our N? I want to take you back to the formula page in your paper 2. There is a formula there. N, the number of moles, equals to the number of electrons divided by your Avogadro's constant. And we have our Avogadro's constant as 6,02 times 10 raised to the power 23. Please, I need you to get this because this might occur so many times. N is the number of moles. All right, let's write this formula. N is the number of electrons over Avogadro's constant. So this is actually the formula, the N that we need here, although it's written capital in one place and written as a small letter in the other. All right, so we know our number of moles of electron as 1,008. So if we calculated that 1,008 equals to, this is number of electrons we're looking for, and this is the Avogadro, which is 6,02 times 10 raised to power 23. So our n should be 1,008 times 6,02. Okay, I want us to do our calculation at once. Now we know that our Q equals to NE, but basically we know this is what we actually mean now. All right, but it's not written like this on the formula page, it's written this way. So our N is 1,008 times 6 times 6,02 times 10 raised to power 23, and the charge on an electron, if we go back to our table of constant, is 1,6 times 10 raised to power negative 19. 1,6, we do not really need the negative sign here. The negative simply tells us that electrons are negatively charged. So times 1,6 times 10 raised to power negative 19. All right, so put that in your calculator, and we should have 9,707 columns. This is quite long. Q therefore equals to IT. So 9,707 should be equal to, we're looking for that, multiplied by 3,600, 1 hour. Our I therefore 2,70. Okay, I know this is quite long, but I'm going to take you through again just to help us understand what we did. Now, all right, we said that 1 mole here from a balanced equation will always require 2 moles of electron. But originally we have 0,54504 moles deposited, and that would need 1,008 moles of electron. All right, so we have our number of moles of electron, which we would use to calculate the quantity of charge. All right, so, but first we need to use that to get the number of electrons. Please, let's be careful with this capital N and the small n and this small n. They're quite different. This capital N is this, right? I mean, it should have been better if we have it this way to create clarity. And this is the number of moles which we got as 1,008. Avogadro's constant, and then we get the number of moles, the number of electrons. Actually, it's called number of particles, if you remember your grade 10. And then we substitute all that, we get our Q, and bring it back into this equation to get, how many marks is this altogether? It's quite long. 5 marks, so it's worth it. It's worth it. I hope that's well understood. You could rewind over and over again to make sure you get the concept of the calculation. Very good calculation. Okay, let's roll on to another question. All right, here we have another question. And we're running through again, hoping that you are done with your own. Now the medal Natasha won for 3rd place. Third, it's 3RD. It doesn't contain as badly tarnished, and she wishes to coat it with copper. Already, if she's coating with copper, with the copper electrode there, and with the copper salt, draw a fully annotated diagram indicating the apparatus and chemicals Natasha would use to coat the metal. 6 marks. Wow. Annotated, a fully annotated diagram. Oh, okay, I'm running out of space here, but we can simply do that in the small space. Annotated diagram means we need to show everything. All right, let's have our metal. We know we need a copper electrode. Okay, the metal has to be connected to, that's where reduction would take place. Let me make this a bit wider to create enough space. The metal has to be immersed completely. All right, that's where reduction will take place. So it's positive here and it's negative. All right, awesome here. So this is, we need to label our metal. What do we have here? We have a copper electrode. Remember, electrons are lost from the anode. So since they said annotated, we need to show that electrons are moving in that direction. What else? Our electrolyte is a copper salt. It could be any copper salt, CuSO4. It's a capital C, CuSO4. What's going to happen? Annotated means explain with diagrams. I'm going to have Cu2 plus there, and I'm going to have Cu2 plus also going in, and that's a 6 marks. All right, so it's basically using diagrams to explain what happens. You have your metal on the cathode, your copper electrode on at the anode. Write down the reduction half reaction that takes place during the coating process. That's, we've written that over and over again. That's reduction. Done. Is the metal the anode or the cathode? From your diagram, you can see the metal has to be the cathode. We see at C. 9 marks. Very, very straightforward. 9 marks there. All right, good. Remember the annotated. You need to show everything. I'm sure you're going to have a mark there for showing the direction of electrons. You have a mark for this. You have the mark for this, a mark for that. You have a mark for this. So it's 1, 2, 3, 4, 5, and 6, the metal in the cathode. All right, good question. A bigger diagram of what we just did right now. Just a bigger diagram. Nothing different, just a bigger diagram of what the question we answered about Natasha's metal. Okay, here is another question for us to handle quickly. This, we should be able to get now this correctly because we've been running through quite a number of them. Right. The diagram below represents the apparatus used in the electrolysis of copper 2 chloride solution. A and B are 2 carbon electrodes connected to a power supply. Right. If they are connected to a power supply, remember your anode should be this and your cathode should be that. Which electrode, A or B? All right. Remember that we said it's EEC, you have AC positive. Our anode should be positive. So which electrode, A or B, is the anode? Our answer is A. A is the anode because it's the positive. Is this electrolytic process endo or exo? We said that this is not spontaneous, so it must be an exothermic. If it was spontaneous, it would be exo. But electrolytic cells are not spontaneous. They are driven by electrical energy from a DC supply. Write down 3 observations that can be made during this process. All right, since we are using carbon, what's going to happen? Let's quickly explain. You have CuCl2. It breaks down into Cu2 plus and Cl minus. Okay, before we write down the answer, let's understand. This guy would run through the cathode, and this one will run through the anode. Okay, there will be oxidation here, and there will be reduction there. Okay, let's see. All right, now let's see. At the anode, what is the observation? Now our answer. Chlorine gas will be evolved. I'm sure if you go back to the video, you'll get why chlorine gas is evolved. It's simply because there is oxidation there, and oxidation, remember, is the loss of electrons. So that's why we have chlorine gas as a product. All right. At the cathode, what are we going to have? We are going to have, because it's what we observe, we are going to observe a brown solid deposit. Copper is brown of copper solid due to reduction. Let me just write that to help us understand why that will happen. Good. And thirdly, what's going to happen is that, remember, we're using copper 2 salt, which is naturally blue. The electrolyte, or the blue color, if you go back to the video, we mentioned this, the blue color of the electrolyte fades because Cu2 plus is depleted without replacement. All right, Cu2 plus is depleted without replacement. I hope we understand that. Write down the overall cell reaction. Actually, we've done that already by writing um, this, but let's put it down. If we combine this equation and this equation, what are we going to have? It's 2 electrons on the left, 2 electrons on the right. So what are we going to have? We're going to have Cu2 plus 2 Cl minus to give us what? Cu plus what? No, let's go back and just make sure we write the correct thing. It's, all right, Cl2 gas produced here. So that's it. Balanced, because it's 2 chlorine there, 2 there, copper there, and copper there. So we balance. That's our overall cell reaction. This is just your redox, oxidation and reduction, half cell reaction put together. Give one reason why the salt needs to be in solution in this process. When we define electrolyte, we said it must be an ionic solution. This is to allow free movement of ions. Your ions must have free movement, to allow free movement of ions. Again, questions done. Very, very easy question to work with. Now let's move to the next question. All right, another 13 marks question here. All right, we've paused, answered. Let's mark. A hydrogen-oxygen fuel consists of an electrolytic solution such as potassium hydroxide and 2 inert electrodes. Hydrogen and oxygen are bubbled into the cell, and the following half reaction occurs. Write down the overall reaction of the cell. Overall, we know one of them is reduction and the other one is oxidation. So what do we need to do? We need to balance. Okay, let's see. All right, let's balance. All we need to do is simply to multiply this by 2. So we're going to have 2 hydrogen there. All right, and I'm going to have what? 4 hydroxide ion. All right, on the left, and on the left here, what do I have? I have oxygen. Okay, let's emit space. That looks like it's going to be long. I have 2 hydrogen. I'm sure you know where that came from. The 4 hydroxide ion, you know where that came from. The left, plus oxygen gas, plus 2H2O. And on the right, what are we going to have? 4H2O. All right. Already my 4 electrons and my 4 electrons cancels out, and I have 4OH minus. But if you look at the left, we have 4OH, we have 4OH. If you move 1 over, we can simply cancel that out. That's what we did to the electrons as well. You have water here, you have water here. We cannot have water as both product and that, so we need to move this. Let's move this over here, because this is where you have abundance. So it's going to be 4 moles minus 2 moles, which is 2. So our final answer will be 2 hydrogen plus oxygen to give us what? 2H2O. This is liquid, this is gas, this is gas. Remember, it says hydrogen and oxygen were bubbled. All right. Give a reason why this is regarded as environmental friendly. Number 1, we're using inert electrodes. And if you look at the products, we are actually producing water. Water is the only product, so it is environmentally friendly. Water is the only product. I mean, who runs away from water? Water is the only product, so it is environmentally friendly. Okay, calculate the initial EMF of the cell. Again, it is E cell equals to E cathode minus E anode. Now the question is, what is going to be our anode and what is our cathode? Let's look at it carefully. Let's go back. Which one is our cathode? Uh, this here, oxidation, is the loss. So this is oxidation and that is reduction. So we need to go back to our tables and find these values. Okay. Alright, it's going to be easier for you with your table by your side. Uh, let's find, we need water, we need hydrogen and hydroxide air. Let's find that first quickly. Let's go to our table. We need water. Oh, here it is. We have water here, we have hydrogen and that is negative 0.83. So negative 0.83 there. And let's find the reduction. We need oxygen, we need water, and that. Okay, let's go find our reduction quickly. Let's go find our reduction. Okay, here we go. I think it's what it's what we're looking for. 0.4. So this is positive. Remember, the more positive one is the reduced one. So that confirms our answer. So here now we're going to have E cathode as 0.4. It's more positive, minus 0.83. And what would that answer be? 1.23 volts. All right, perfect. Calculate the energy stored. This is another type of calculation. Energy stored, if the capacity of the cell has a capacity of 1, I want you to see that. 1 amp hour. 1 amp hour. Already, we're given that I equals to 1, and our T equals to 60 times 60. We're looking for energy. Again, this is a physics formula where we know that W is equal to V I T or V Q. Remember, our Q is IT. Okay, but it's very simple now because let's use this one. We have our V as 1.23. We have our I1 and we have our time. Very, very straightforward, but you might not know that that's the formula to use. And if you multiply that, what you have 4,428 joules. Awesome, awesome calculation. I'm glad we're running through this session. You must be lucky to have found this video to help you deal with these strange calculations that we should be expecting in our exams. All right, this question is also done. Let's run through another one. Okay, here we have another question. I think it's about the 6th or 7th. Wow, this is quite a very valuable session. You need to keep this video, you know. Okay, we have that. And then let's scroll down for you to be able to answer the question. So you need to move up and down answering this question. Okay. Let's see. The apparatus below is used to demonstrate the electrolysis of a concentrated sodium chloride solution. Both electrodes are made of carbon. Where did we say that this looks like our chloralkali industry? Both electrodes are made of carbon. A few drops of universal indicator added to the electrolyte. Now that's your acid and base. The equation for the net reaction is given as that, and we have that. All right. Initially, the solution has a green color. Universal indicator becomes red and acidic, and purple in alkaline. Purple in alkaline. Okay, red and acidic. Define the time electrolyte. Electrolyte is, we know 9.1. Of course, we know it's an ionic solution. that allows electricity. Let's use the word conducts. Alright? That conducts electricity through the movement of ions. We define this while explaining the movement of ions. Right? Ions must be free to move. Okay. Now, when the power source is switched on, the color on the electrolyte around Y changes from green to purple. Let's see. If it changes from green to purple, so we have a purple coloration here, then there must have been an alkaline, and our alkaline is simply represented by our OH. Let's go back. Do we have OH in the equation? Yes, sodium hydroxide is produced there. Good. We have a headway. All right. Write down the half reaction that takes place at Y. Okay. Now, in this case, you would notice we were not even clear about the cathode or anode, but we know that this OH must be coming from water. So, water needs to be reduced. Water needs to be reduced. And if water is reduced, let's see quickly. Alright, so we know water is reduced. Let's go to our table. Let's go to our table to find water. Right, just right staring at our face there. We have water plus 2 electrons. That's reduction. Again, we have hydrogen gas and OH. Remember, OH is what we actually turn in for. So it's 2H2O plus 2 electrons. You have hydrogen gas. Alright, so this is why we have a purple coloration there. Okay, that's quite nice. Name and formula of the gas produced at X. At X, our X is the anode. We have sodium chloride. Alright, so our answer is just going to be chlorine gas. Chlorine gas. Please go back to the video. We did quite a whole lot of explanation on this. Chlorine gas would be produced there, because here already we have hydrogen gas. Okay. Refer to the table to explain why hydrogen gas and not sodium is formed at the cathode. Okay, let's go back to the table. We have water here, negative 0.03, and here we have sodium, negative 2.71. I need us to write those values, 0.3 and 2.71. This one is negative 0.83 and negative 2.71 sodium. All right. Which one is stronger? Let's go back. Now, if you look at the table here, it says increasing reducing ability. So we are saying that this one is increasing oxidizing ability. Sodium is a stronger reducing agent, so it will reduce water. That's just it. Sodium is a stronger reducing agent. It will reduce what? Water. So we need to check the strengths and use that to answer the question. We can so we can say water is a stronger, either way, either we use water, oxidizing agent. Water is a stronger oxidizing agent than Na plus. Okay, therefore it will be reduced to hydrogen gas, because we must talk about what is formed. Or use the other way around to say that sodium plus is a stronger reducing agent, so it will reduce water to hydrogen gas there. All right. All right, so we've run through a few questions. We would have a second session to look at more questions on electrolytic cell. But I need us to go through the things that we've done to make sure that we understand them. All right, it's an honor to have served again, and it's Bishop again signing out on behalf of Krazifizix. We would, at the next session, just so that these files are quite small for us to use on our phones, uh, we need to make it small. All right, but you know you can always reach us at 078-071-7507. Get your school to call us, your principals would come and run classes with you. All right, thank you, and just wait for the next session.